Hi, in today's class, we are going to discuss the concept of eddy currents. Now, generally, before I start discussing this topic, I often prefer to ask you the question, who discovered eddy current? And students every time says it was discovered by Eddy. That's a wrong answer. Because eddies means ripples. If you look at the word eddies, the meaning of eddies is ripples in water. Ripples. Eddies means ripple. Or they are just like the whirlpools, I would say. Now let us take into consideration this point. Now see here, I have drawn a uniform magnetic field B. And now I am making this plate, a rectangular plate, to enter the field with a velocity V. Now if you look at this rectangular plate, you can see that this much part is already in the field. Okay. Considering just like a rod as we have seen in the previous class. So this part can be treated like a rod moving with a speed v or with a velocity v. As we all know, when this moves with the velocity v, so I will teach you one point, that's a right hand rule. Left hand rule we are seeing the moving charges and magnetism. Now we are going to see the right hand rule. And according to the right hand rule, thumb represents the direction of motion. Obviously, this has to be the direction of magnetic field and this is the direction of the induced current. I repeat, motion, magnetic field, induced current. Repeat please, motion, magnetic field, induced current. Now this is moving rightwards. So the direction of the induced current here is upwards. As we said, this part will behave like a cell of positive terminal and this is negative terminal. Now, as a result of developing a current here, this current will circulate in this path. Here, this current will circulate like this. And if you look at this one, this resembles like ripples in water. Ripples in water. And this kind of currents are called eddy currents. So how will you define these eddy currents? Eddy currents are swirling like currents. These are swirling like currents. Observed in bulk metals when they are subjected to a very magnetic force. Now see, show you a situation where a conducting plate is made to oscillate in this magnetic field. Now as a result of this current, according to Fleming's left hand rule, this side will experience a force in this direction, right? A force will be developed in this direction because according to Fleming's left hand rule, current is upwards, magnetic field is in the board, so magnetic force is here, so it is coming to velocity. When it is completely inside the field, only has got a velocity, but here the induced current is equal to 0 because once it is completely inside the field, there is no change in flux intercepted by this plate. So there will be no induced EMF here. And now it comes out. Here you will have velocity V dash. My question is V dash greater than V, V dash equal to V, or V dash less than V? Surely V dash will be less than V. Why? What's the reason? Because there is a damping force here. Because there is an opposing force here. So it will come out with a reduced velocity. So V dash is obviously going to be less than V. Now I can say here V dash is going to be less than B. Now in the next equation, the same plate will, okay, it will go to the other extreme position and it will come back. It will come back to the field. But this time we will have a velocity V double dash. Clearly V double dash is going to be less than V. So what ultimately happens during the oscillation of this plate? It will oscillate with a decreasing velocity, which means it will oscillate with a decreasing amplitude of oscillation. Right? It will execute oscillation with a decreasing amplitude, just like a simple pendulum oscillating in the presence of air resistance. A simple pendulum oscillating in the presence of air resistance, which means one of the important consequences of eddy currents. Coming to the consequences of eddy currents, I will say the first and most important consequence of eddy currents is eddy currents produce damping. Eddy currents produce damping. So this is the most important consequence of eddy current. The second thing, as this conducting plate, although I said it's a conducting plate, there is no perfect conductor at room temperature at normal conditions. That means there may be some or the other kind of resistance associated with every conductor. Some or the other kind of resistance associated with every conductor, which means there will be heat. Eddy currents will have another effect, that is another heating effect also. So what causes the heating effect? The heating effect is constituted as I square RT. This current I is the eddy current. This current I is eddy current. So what are eddy currents? Let us just quickly revise what we said until now. Eddy currents are swirling like currents observed in bulk metals. That means metals having sufficient surface area. Bulk metals when they are subjected to a varying magnetic flux. When these conductors are subjected to a varying magnetic flux, that is where eddy currents are observed. And what are the important consequences of eddy currents? Eddy currents will produce damping. Why? According to Lenz's law. Then another important thing is eddy currents produce heating. How? I square RT is the amount of heat produced. What is that I here? I is the eddy current. I is the eddy current, and such losses are called I square RT loss or Joule's heating effect. Now that means it is not desirable. Eddy currents are not desirable in all situations, and it is important to minimize. That is the word I use only. I cannot cancel or I cannot avoid eddy currents completely, but I can minimize eddy currents. How can eddy currents be minimized? Okay, I'm just taking the previous example or previous figure which I have shown here. So again, what I'm saying is that I can minimize eddy current losses or heating effect of eddy current. How? As I told you, this much part is inside the field and this goes to velocity V, and this current is down here. Right. So I square R loss or Joule's heating effect, this I want to minimize. How can I minimize this I square R loss? Just by minimizing I. Now the question, how can I minimize I? How I can be minimized? Very simple. I have to break this conducting path has to be broken. Conducting path has to be broken. Then only the current can be broken. How to break the current? Current needs to be broken. So what I will do? I will just cut this plate into small, very small strips. This plate is cut into very small strips. How? Normally, I am placing the knife in the direction of the magnetic field. The knife is placed in direction of the magnetic field. I am keeping the magnet in the direction of the magnetic field, and the plate is cut into, or plate or the bulk conductor is cut into infinitesimally small strips. That means now you are having this kind of pieces on this, right? You are having this kind of pieces. The bulk conductor is closed. So what I need to do next? But I need this bulk conductor solved. That is important for me, but at the same time I want to minimize eddy currents also. I want to minimize eddy currents, at the same time I need this bulk conductor also. Then what should I do? I will join them. Now these strips I am going to paste together. I am taking the first strip, I am taking the second strip, I am taking the third, fourth one, fifth one, so on. How I am going to paste it? I am going to paste them by means of an insulating adhesive. Insulating adhesive. Insulating adhesive. Means what? These two are joined by an insulating adhesive. Suppose a current is developing here. A current is developing here. Now there is an insulator in between. A current is developing here. Now when it comes here, what happens? What happened? Come on, bro. What happened here? This is an insulator, right? Will current flow? No way. So just like the way, as I said, eddy currents are minimized by this way. How? Cut the bulk metal into infinitesimally small strips and join these strips by means of an insulating adhesive. Join the strips by means of an insulating adhesive. By that way, eddy currents can be minimized. Ready? Now moving on to the next aspect, that is regarding the uses of eddy currents. The first application is, okay, not according to the NCERT order, damping in meters. So eddy currents are, so generally in meters damping is important because we are, okay, suppose when we use a voltmeter and the needle is deflecting likewise, will it be possible for you to take the reading correctly? No. So when the needle is deflecting likewise, you are unable to take the reading properly, which means you have to get that reading properly. This can be accomplished by having this damping effect in meters, and such damping effect is produced by what I will say, eddy currents. Eddy currents are the ones which produce this damping effect. The second application I would say is that a magnetic braking. So magnetic brakes in trains. Let me tell you, the rails are conductors. Rails are conductors. Now these magnetic trains, these high speed trains are moving above this rails, I would say. And the bottom part of this train may contain what I would say powerful electromagnets. Powerful electromagnets. The bottom of the trains contain powerful electromagnets. Now, I want to apply brakes onto a train. What will do? When brakes are applied, these electromagnets are magnetized. How? A current is passed through these coils. The coils will get magnetized. In this way, the electromagnets are magnetized. Electromagnets are magnetized. Electromagnets are magnetized. Now, as a result of the magnetization of these electromagnets, eddy currents will be set up in these rails, I would say. Eddy currents. And according to the Lenz's law, the direction of the induced current is to oppose. What is the cause here? So, actually the current here is a constant way. Due to the motion of this train, the flexi link with these rails are changing. Flexi link with the rails are changing. So, what happens here is that as a result of the motion of the train, the flexi link with the rails are changing. So, cause of the induced current is the motion of the train, and that should be opposed. And that will be opposed by producing an eddy current. Since there is no physical contact involved, there will be no loss or negligible loss of energy in the process because there is no wear and tear occurring here. There is no wear and tear. That is application number 2. That is magnetic waves. The third application is induction furnace. It's a device where alloys are prepared. A device for preparing alloys. Okay. Let me consider a particular metal. This is my physical visualization only. Now, it is wound on by means of a coil, and we apply a very high frequency current. High frequency current. Now I can say that in this current I is equal to d phi divided by r dt. Now high frequency means dt will be very small. Dt is going to be very small as a result of high frequency. dt is very small means what about I? Large I. So as a result of small dt, a large current will be induced here, which means the heat produced is equal to I square RT, or I square I am saying I square RT, or at time. Now I is a very large quantity. I is a very large quantity. Heat will be very large. So it is going to be very large heat produced. Very large heat will be produced here. Very large. As a result of this very large heat, that will be sufficient to melt this metal. The heat produced in this one will be sufficiently large enough to melt the metal in that way. What I have to say is that heating is produced in an induction furnace. Now we will say that the next application is it is also used in electric meters. That is the old type analog meter. Analog. So there you used to find a disc is rotating, not in the new meter which is a digital one. The earlier meters, maybe a meter that we were used to see in our homes for before last 5 years or so. In such meters, what happens when current is passed through the meter? There will be electromagnets present. As a result of this varying current, when we use different devices will consume different current. So as a result of different current, what happens is that these electromagnets will get magnetized. As a result, an eddy current will produce on the disc. Now as a result of the current on the plate, it will experience a torque. The torque experience is directly proportional to I, current consumed by the household devices. When you consume more current, it will produce more rotation, just like the way the reading is taken. So these are the aspects I want to say regarding eddy currents. Hope it is clear to you. Thank you.